Okay. All right. So we defined differential forms on a smooth manifold last time. And today we'll talk about the integration of differential forms on a manifold. So for omega a 1 form on a manifold M, we defined its integral over a curve gamma in the manifold. So the integral of omega over gamma was defined to be the integral of the following function. So at each point t, you look at the tangent vector to the curve gamma prime t, and so omega can act on that tangent vector since it's a linear functional on each tangent space. So you look at omega at gamma t acting on the tangent vector gamma prime t. This gives you a function of t. You integrate that from 0 to 1. Okay. Now for higher dimensional forms, if you take a K form in general, the objects we will be integrating K forms over will be what are called K cubes. So that means you take the unit cube, so 0, 1 to the power K, and a K cube is a smooth map from, say, C from 0, 1 to the power K into the manifold. Okay. So it will be some, oh, sorry, it's a 2 cube. Yeah, sorry. Some curved cube sitting inside your manifold. Okay. So say this could be the manifold. Okay. And we want to define the integral of omega over this parametrized K cube. Okay. So how do we do that? Well, what we can do is we can pull back the form omega here to get a form on the unit cube. So you look at C star omega. So this is a K cube, a K form on the unit cube. Okay. And so it's a K form in K dimensions. So it's going to be pointwise. At each point, it's going to be a multiple of dx1 wedge dxk. So this is equal to some function h dx1 wedge dxk. Okay. So h is a smooth function on the unit cube. Okay. And then you define the integral of omega over the K cube C to be the integral over 0, 1 to the K h dx1 dxk. Okay. So how do we see this as a generalization of this example for K equal to 1? Well, what is this function h? So to compute this function h, you evaluate both sides of this equality on the basis E1 to EK, right? So then we get that C star omega at a point x in the unit cube applied to E1 to Ek is equal to h of x into dx1 wedge dxk applied to E1 to Ek, and dx1 wedge dxk applied to E1 to Ek, this is just 1, so this becomes h of x. So we get that h of x is equal to c star omega applied to E1 to Ek. And so that, by definition of the pullback, is equal to omega at the point c of x applied to the derivative dc at x applied to E1 to Ek. Okay. Here, see, the derivative, by definition of the derivative of a smooth map between manifolds, this goes from the tangent space to the unit cube, which is just Rk, to the tangent space at c of x to m. Okay. So this is the function h of x. So we're integrating this function. Okay, so the integral of omega over c, this is equal to the integral over 0, 1 to the k, omega at c of x, dcx E1 up to dcx Ek dx1 dxk. All right. So here I should have said this C is a smooth map. So this is called K cube. In M. So is the definition clear? Just 1 second. Okay, so is the definition clear?
That's clear.
All right. So more generally, we can define like we do in homology, we can look at the free vector space on the set of singular K cube in M. So a singular K cube is a smooth map from the unit cube into M. And then the space of singular K chains is defined to be the free vector space on the set of singular K cubes. So these are formal sums, summation alpha I Ci, finite formal sums, where the alpha i's are real numbers and the Ci's are singular K cubes. Okay. So just like in homology, you have singular simplices, right, in your manifold, and you look at the K chains are formal sums of singular simplices. So similarly, instead of singular simplices, we're looking at singular cubes. Okay. And then for a singular K chain, the integral extends by linearity. So the K cubes form a basis for the space of K chains, and we've defined the integral on this set of K cubes. So it extends uniquely by linearity to a linear function on the space of K chains, right? Okay. So the integral of omega is defined over any singular K chain. All right. Okay. Okay, so for a chain sigma equal to summation alpha I Ci, you define the integral of omega over sigma to be summation of alpha integral omega over Ci. Okay. So this integral of omega, this defines a linear functional on the space of K chains, right? So if we call the space of K chains Ck of m, then this defines a linear function. Sigma goes to the integral of omega over sigma, right? Okay. So this defines a linear map, capital Phi, from the space of K forms, omega Km, to the dual of the space of K chains. Okay. Omega goes to the integral of omega. Okay, so just like in homology, the dual of the space of K chains is called the space of cochains. Okay, K cochains. So we have a linear map from K forms to K cochains. Is this clear?
Sir, can you please repeat? What do you mean by the dual of K chains?
Well, this CKM is a vector space, right?
Okay. Yes.
So just its usual dual, the set of linear functions from the vector space to R, right?
Okay. Nice.
Just the dual space of a vector space, right?
Yeah, that's fine. I'm just trying to see how does it look like. Okay.
Yeah. So it's some infinite dimensional vector space, all right? It's some infinite dimensional vector space.
Okay.
There's no norm on it. There's no norm, nothing like that. It's just some abstract infinite dimensional vector space. Okay.
So it's the continuous dual you are taking, right?
No, it's not the continuous dual. There is no norm. It's not the continuous dual. It's the algebraic dual. It's not the continuous dual. It's the algebraic dual.
Oh, I see.
Just the full dual. Okay. So no continuity assumption, nothing. It's the full dual. Okay. There's no norm on CKM. So we can't define, there's no topology on CKM. So we can't define a continuous dual anywhere. All right. It's just the algebraic dual. Okay. So, so the space of K forms maps linearly to the space of K cochains, right? Omega goes to the linear functional integral omega. Is this clear? Yes?
Yes. So the linearity follows by the linearity on integration, right?
Right.
Yeah, it's clear.
Okay, so we have this linear map. Now the claim is this linear map is one-to-one. Okay, so that the K forms are actually going to be identified with the subspace of the K cochains. Okay, so how do we see this is one-to-one? So we can see that as follows. So given a singular K cube C, for epsilon in between 0 and 1, we can define a singular K cube C sub epsilon. So C sub epsilon of x is just C of epsilon x. Okay. So if this is your C, then C sub epsilon is essentially given by mapping the whole cube into the cube of side length epsilon and then composing with C, right? So C epsilon will be a very small cube inside your cube C. Okay, this will be the image of C epsilon. All right. This is sitting inside M. Okay, is this clear? Yeah. Okay. So now suppose this point P is equal to C of 0. Okay. And suppose that the derivative at the origin of C maps the basis vectors EI to some tangent vectors VI at the point P, right? Okay. Then this small cube is going to be, the sides are going to be, for epsilon small, the sides are going to be approximated by the vectors epsilon VI, right? Okay. So what happens when we integrate over this small cube? Well, let's work out the integral over this small cube. So first, let's look at the derivative of C epsilon at x applied to EI. So by the chain rule, this is going to be the derivative of C at epsilon x applied to epsilon EI, right? Okay. I mean, the derivative of the map x goes to epsilon x is just multiplication by epsilon, right? It's a linear map, so its derivative is itself. And it is just the multiplication by epsilon. So by the chain rule, this is going to be dc at epsilon x applied to epsilon EI. And by linearity, the epsilon comes out. So this is going to be epsilon times dc at epsilon x applied to EI. Okay. So now let VI be dc at 0 applied to EI. So if I look at the integral of omega over C epsilon, and I divide by epsilon to the k, then what is this? This is 1 over epsilon to the k. The integral over 0, 1 to the k. And then I have to take omega at C epsilon of x. So that's C of epsilon x applied to dc epsilon at x of EI, right? I goes from 1 to k. So that will be epsilon dc epsilon x E1 up to epsilon dc epsilon x EK, right? So now by multilinearity, these k epsilons, they come out as epsilon to the k, which cancels with this epsilon to the k. And then I get the integral of over 0, 1 to the k, omega at C of epsilon x into dc sub epsilon x E1 up to dc epsilon x EK, right? Okay, so now we use the fact that the map, the cube is a C1 map. So as epsilon tends to 0, these dc epsilon x E1 up to dc epsilon x EK, these are tangent vectors based at the points C of epsilon x. Those will converge in the tangent bundle to tangent vectors dc0 E1 up to dc0 EK, right? Since C is a C1 map, all right? And this omega at this C of epsilon x, so applied to these vectors, that will converge to omega at P applied to V1 up to Vk, right? So this function of x, it converges to the constant omega P V1 to Vk. So when you integrate over 0, 1 to the k, you just get omega P V1 to Vk. All right. Okay, so that means that the value of omega at a point P applied to tangent vectors V1 to Vk, we can get as a limit integral omega over C epsilon into 1 over epsilon to the k, right? Limit epsilon tends to 0, where C is any k cube. so that C of 0 is P and DC0 is DC0 of EI is VI. I goes from 1 to K. All right. So from this, it follows easily that this linear map from K forms to K cochains is 1 to 1, right? Because if omega is a K form whose integral over every K chain is 0, then its integral over every K cube is 0. So if I take any point P and tangent vectors V1 to Vk at P, then we can always choose a K cube C, so that C0 is P and DC0 of EI is VI. And then omega P at V1 to Vk, this is the limit epsilon goes to 0, 1 over epsilon to the K, integral of omega over C epsilon. And this is 0 because the integral of omega over any K cube is 0. So therefore, omega applied to any K tangent vectors is 0 at any point. And so omega is identically 0. Is this clear?
Yes, sir, it's clear.
Okay, so the kernel of this linear map is trivial. So this linear map is 1 to 1. Okay. Okay.
So omega P V1 up to Vk is exactly how the elementary volume form is changed under the full vector.
Sorry, I didn't understand.
Like omega P V1 up to Vk. This is sort of the elementary volume form.
What is the elementary volume form?
I mean not elementary, but like so what I wanted to mean is that like at P no, sorry. I wanted to say.
Omega is just some K form, right? At each point, it is just some K multilinear, alternating multilinear function on the tangent space.
Yeah. Fine.
Okay. All right. Okay. This is just the value of omega at P applied to K tangent vectors V1 to Vk, right? That's all. Nothing more.
Yeah.
Okay. The point is we can write this as a limit of integrals over small cubes divided by an appropriate factor 1 over epsilon to the K. All right. Okay. So now let's define, like we do in homology, the boundary operator, right? So you would have seen this for singular simplices. So we can define the boundary operator similarly for singular K cubes. So first, so a cube, what's the boundary of a cube? So a cube will have 2K faces, right? So K cube has 2K faces, right? So for example, if this is your coordinate, say x1, and this is say this coordinate is x2, and this coordinate is x3, then what are the faces of the cube? So for example, this bottom face here will be x3 equal to 0. And this top face will be x3 equal to 1. Right? So in general, the faces are going to be xi equal to 0 and xi equal to 1. I goes from 1 to k, right? These are your 2k faces. Okay. So using these, we can get 2k singular k minus 1 cubes, right? By restricting our our singular k cube C to each of these 2k faces. Okay, so we define for I in between 1 to k and alpha in the set 0 to 1, 0, 1, the C I alpha face. So that's a k minus 1 cube. So C I alpha of x1 to xk minus 1, this is defined to be C of x1 to xi minus 1, and then you put an alpha in the ith spot, and then you have xi to xk minus 1. Okay. So alpha is either 0 or 1, right? So we're essentially restricting C to one of the 2k faces of the unit cube. All right. And then the boundary of C, this is defined to be a k minus 1 chain. So it is a formal sum. I goes from 1 to k, alpha goes from 0 to 1. And then you have to take the correct sign for each of these faces. The correct sign turns out to be minus 1 to the I plus alpha, C sub I alpha. Okay. So this is the boundary of a k cube. It is a k minus 1 chain. So this defines the boundary operator on k cubes, which form a basis for the k chains. And then by linearity, the boundary operator extends to a linear map from the k chains to the k minus 1 chains. Okay. And then just like you prove in when you compute homology, the square of the boundary operator, that means if I apply the boundary operator twice from ckm to ck minus 2m, this is 0. Okay, so you can work out this calculation as an exercise. The idea is that when you look at the boundary of the boundary, right? So you're going to look at from faces, you'll get to edges, right? So each edge in boundary squared of C, this occurs twice in boundary squared C with opposite signs coming from two faces in boundary C. So for example, this edge is going to come from as the boundary of this face and also from as the boundary of this face, and it will come with opposite signs. Okay, once it will be going this way and the other time it will be going this way. Okay, and so these two will cancel out when you look at boundary squared of C. Okay, that's the idea. Okay. So now we have the boundary operator from k chains to k minus 1 chains. So therefore, if I can look at its dual of the boundary operator, so del star, that will go from the dual k minus 1 cochains to k cochains, right? The dual will go in the opposite direction between the dual vector spaces. And now the natural question is the following. See, we've seen that the k minus 1 forms, they embed into the k minus 1 cochains, and similarly the k forms embed into the k cochains, right? Via integration. So the natural question is, does the dual of the boundary operator send the subspace of k minus 1 forms to the subspace of k forms, right? Yes? Okay, this is a natural question. Yeah. And the answer turns out to be yes. In fact, the dual of the boundary operator actually turns out to be a first order differential operator, D, called the exterior derivative, which will go from k minus 1 forms to k forms. Okay. So let us see how this exterior derivative is defined. So let D be an open set in Rn, and suppose omega is a k form on D. So it's of the form sum over multi-indices I bar. So I bar is a multi-index I1 up to Ik, where the IKs are, the I's are in strictly increasing order. and sum over I bar, A I bar, dxi bar, right? Where dxi bar is shorthand notation for dxi1 wedge dxik. Okay. So now we can do the following. I take a point P and D and I look at a k plus 1 cube. Okay. So such that C0 equal to P and DC0 of EI is some vector VI in Rn. Then what we can do is we can look at the boundary of, so I look at C epsilon, right? That's a small k plus 1 cube. So I can look at its boundary, right? Its boundary will be a small k chain, right? Because C epsilon is a k plus 1 cube. So its boundary will be a k chain. So you think of boundary of C epsilon, that is a small k chain. I integrate omega over that. It turns out that this integral, as epsilon tends to 0, if I divide by epsilon to the k plus 1, this converges to a finite limit. Okay. Which only depends on the vectors Vi, which are the images of Ei under the derivative of C at 0. Okay. So this, and it turns out to be given by actually a form called d omega at P applied to V1 to Vk plus 1. Where what is this form d omega? This is the sum over I bar, d of ai bar wedge dxi bar. Okay, so this is a k plus 1 form, which is called the exterior derivative of omega. Okay. So how are we getting the exterior derivative? Well, geometrically, how we're getting it is, you take, so say, for example, if omega is a 2 form, say D is a domain in Rn, an open set in Rn. Okay. And I take a point P in D, and I take vectors V1, V2 in Rn, and I take C, a 3 cube, mapping into D. Sorry, if I take 3 vectors here, 3 vectors, V1, V2, V3. Yeah. And so let me say that C, so I take this 3 cubes such that C0 equal to P and DC0 EI equal to VI. I goes from 1 to 3. Okay. Then what do I have? So here's my point P. I have 3 vectors, V1, V2, V3. Okay, there's less than a minute. Let me just stop this session and start a new one. Okay. Okay, so let's start. So what are we doing? We're taking C, which is a 3 cube here. Okay. And then we're looking at the small 3 cube C epsilon, right? So C epsilon will be some small 3 cube here with sides almost tangent to V1 to V3. Okay. And now the boundary of C epsilon, that's a small two chain, right? I can integrate omega over the boundary of C epsilon, right? Okay. Now notice something. The boundary of C epsilon, right? Well, each of the faces have sides of order epsilon, right? So their area will have order epsilon squared, right? So when I integrate omega over the boundary of C epsilon, a priori, I would expect some quantity of order epsilon squared. Okay. But actually what happens is when you're integrating over this small boundary like this, okay, the boundary faces come in pairs, right? So there'll be an integral over a top face, and then the integral over the bottom face will come with the opposite sign, right? So these two faces will come with opposite signs, and the value of omega here and here applied to vectors here and here will be close. So what will happen is you'll get sort of a difference of values of omega between top face and bottom face. So it's something like taking a derivative of omega in this direction. So you'll get essentially derivatives of omega in all these k directions, you see. Okay. And so what will happen is this integral, instead of being of order epsilon squared, it will actually, because of this, there'll be some cancellation here. You'll get a quantity which is of order epsilon cubed. Yeah. So this is of order epsilon to the 2 plus 1. So you divide by 1 over epsilon to the 2 plus 1. This converges to so if omega is equal to sum over I less than j, a ij dxi wedge dxj, then this converges to the form sum over ij d of aij wedge dxi wedge dxj at p applied to v1, v2, v3. Okay. And this form here is what we're defining to be d omega, the exterior derivative of omega. Okay. So is this clear? What's happening? Yes? Okay. So this is the exterior derivative. And it has the following properties. So if f is a smooth function, then I can look at df, that's a one form, and then I can look at d of df. So this turns out to be 0. So that's not hard to see that d of df is 0. That's the following calculation. So d of df, this is d of, so df we saw was sum over I, del f del xi dxi. And so this will be sum, by definition, sum over I, d of del f del xi wedge dxi. And now d of del f del xi, this is sum over j del squared f del xj del xi dxj wedge dxi, right? So this becomes a sum over ij del squared f del xj del xi dxj wedge dxi. And notice that dxi wedge dxi is equal to 0 because the wedge product is alternating on one forms, right? It is skew symmetric on one forms. So in this sum, I can take the sum over I not equal to j. Okay. And then when I take the sum over I not equal to j, then I can take the sum over I less than j. And then for each pair where I is less than j, I'll get two terms, right? So I'll get one term like this, del squared f del xj del xi dxj wedge dxi. And then I'll get another term interchanging I and j, del squared f del xi del xj dxi wedge dxj. And then I use the fact that the wedge product is skew symmetric on one forms. So this dxj wedge dxi, this is minus of dxi wedge dxj. So then I can group these two terms together to get del squared f del xi del xj minus del squared f del xj del xi dxi wedge dxj. And this is 0 because the partial derivatives commute, right? Okay. So this becomes 0. Is this clear? Yes? Yes, is this okay?
Yeah, this is fine.
Okay, so I'm just going to state some other properties of the exterior derivative. So it satisfies a sort of Leibniz rule, d of a wedge product alpha wedge beta. This is d alpha wedge beta plus minus 1 to the k alpha wedge d beta if alpha is a k form and beta is an L form. And it commutes with pullback. So d of phi star omega is phi star d omega. Okay, where here phi is a smooth map between domains d1 and d2 from from Rm to Rn really. And omega is a k form on the image domain d2. Okay. So using these three properties, one can then show that we have what's called Stokes' theorem for chains in Rn. So if D is an open set in Rn, then for any k K form omega in D, and for any K plus 1 chain sigma in D, the integral of d omega over sigma. So notice d omega is a K plus 1 form. So we can integrate over a K plus 1 chain sigma. This is equal to the integral of omega over the boundary of sigma. Okay, so notice that boundary sigma is a K chain. So we can integrate omega, a K form over it. All right. Okay. So this is Stokes' theorem. So let me just give you the intuition behind Stokes' theorem, why this is true. This is not a formal proof. This is just an intuition. So it's enough to prove Stokes' theorem for sigma equal to a K plus 1 cube C. So what you can do is, so I have C, which is a K plus 1 cube. So what I can do is I can break this up into small K plus 1 cubes. Okay. I divide each side into, say, capital N pieces. Okay. So when I break up the cube into these small pieces, what happens? So notice that then if I look at the integral of omega over boundary C, I can write this as the sum of integrals of omega over small cubes, right? Over the boundaries of these small cubes, right? Because when I take the boundaries of the small cubes, see each, except for the each face which is in the interior of the cube is going to occur twice, right? From two neighboring cubes. So these faces will cancel out, right? When I sum over the boundaries of the small cubes, the only faces which will remain will be in the boundary of the big cube. Is this clear? Right? Yes? Okay. Yes? Is this clear?
Yes, sir. Yes, sir.
Yes. Okay. Thank you. So, so now what can we do for each of these small cubes? Well, by definition of the exterior derivative, this small cube is like one of those, the small cube C epsilon, where epsilon is equal to 1 by capital N. N is a large integer. Okay, so this is going to be approximately 1 over N to the power K plus 1 into d omega at the point, say, the base point of this cube. So let me call that x sub I bar, applied to the vectors dc x I bar E1 up to DC X I bar EK plus 1. Right? Plus some error which is little o of 1 over n to the k plus 1. Right? Okay. Right. This is by our definition of the exterior derivative, right? This exterior derivative applied to these vectors is the limit as capital N tends to infinity of integral of omega over the boundary of this small cube divided by 1 over n to the k plus 1, right? Okay, so therefore this integral is going to be 1 over n to the k plus 1 into this d omega applied to these vectors plus an error term which is little o of epsilon to the k plus 1. Okay. And now when I do the sum, the sum of these terms, what is this? This is nothing but a Riemann sum for the integral of d omega over the cube C, right? This is a Riemann sum for the integral of d omega over the cube C, right? And this term, so let me just, so this is going to be a Riemann sum for, so let me write it like this. This is going to be equal to a Riemann sum for this integral plus what is the error? So I'll have, how many terms are in this sum? Capital N to the k plus 1 into an error which is little o of 1 over n to the k plus 1. Right? Okay. So that gives me a little o of 1. This thing is little o of 1. And this thing converges to the integral. So the whole thing converges as n tends to infinity to the integral of omega, d omega over C. Okay, so that's it. Is this clear? Okay. Yes? Okay. Does this make sense?
Yes, sir.
Yeah, it's okay. Yeah. Okay, so that's just a heuristic for why Stokes' theorem is true. So what does Stokes' theorem say algebraically? Well, look at the left-hand side. This integral of d omega over sigma, this is, so see, we have a bilinear pairing, right, between k-forms and k-chains. So this is the pairing applied to d omega comma sigma, right? And now on the right-hand side, this is the pairing applied to omega and boundary sigma. Okay, but the pairing applied to omega and boundary sigma, by definition of the dual of the boundary operator, this is boundary star, the dual of the boundary operator applied to omega, and that paired with sigma, right? So this is the pairing between del star omega and sigma. So that means the pairing between d omega and sigma is the same as the pairing between del star omega and sigma. This is true for all sigma. That means that these two dual elements, d omega and del star omega, these are the same, right? Okay, so that means that del star is equal to d. So that's what we stated a while ago, that the dual of the boundary operator, first of all, it takes k forms to k plus 1 forms. It preserves the subspaces of forms, right? And secondly, it's given by a differential operator acting on forms. a first order differential operator, the exterior derivative acting on forms. Is this clear?
Yes, sir.
Okay. Yeah, so the dual of the boundary operator is given by the exterior derivative. Okay. And from this, you can see that d squared is going to be 0 for any form, right? Because d squared will be del star squared. And so that will be del squared star, and del squared is 0. So its dual is 0. Okay. Is that clear? So d squared will be 0. That follows from the fact that d is equal to del star and del squared is 0. Is that clear? You don't need to do an extra calculation to see that d squared is 0. It follows directly from the fact that d is equal to del star. Is that clear?
Yeah.
Right? Okay. Once you know that del squared is 0 and d equal to del star, then d squared will also be 0, right? So, okay. So once you have the exterior derivative in Rn, then you can define the exterior derivative on manifolds. So first you define it using a chart. So if M is a manifold and omega is a K form on M, so for a chart U comma phi, first you define the exterior derivative, well, computed in this chart. So let's call it d sub phi omega. So this will be a K plus 1 form on U. So you define it as follows. So, okay, maybe let me just do this here. So suppose now M is a manifold and omega is a K form on M. Yeah. So suppose phi is a chart okay. So so if I have omega here, this is a K form on U. So since phi is a diffeomorphism, any K form on U comes by pullback of a K form on V, right? So there is some K form omega tilde on V such that omega is equal to phi star omega tilde, right? Okay. Yeah. So actually, what do we have? We have if I take the K forms on V, then I have an isomorphism given by phi star to the K forms on U, right? Okay. Now here in Rn, I have the exterior derivative d going from K forms on V to K plus 1 forms on V, right? And I have another isomorphism here, which is again pullback phi star, which is going from K plus 1 forms on V to K plus 1 forms on U, right? Okay. So therefore, from this diagram, I get a map below, right? So that this diagram commutes. Let me call that map d sub phi, okay? So this is the exterior derivative computed in a chart. Okay, so this satisfies that phi star. So if I look at this diagram, right, then d sub phi of omega, this is going to be phi star of d omega tilde, right? Is this clear? Yes?
Yes, sir.
Okay. So now, what is the, how do we compute this? So if phi has coordinates, say x1 to xn, and omega is equal to so say if omega is equal to sum over I bar a I bar dx I bar, right? Then omega tilde has to be, so you see, if this is sum over I bar, sum b I bar dx I bar. So be careful about the notation here. Here the dxi bars, these dxi's are the components of phi. So these are functions on the manifold. Whereas these dxi's, these are the coordinate functions on Rn. Okay, so these dxi's mean two different things over here and here. All right. Okay. So what is phi? So omega is equal to phi star omega tilde. Right. So that is, so when I pull back this form, what is this going to be? This is going to be sum over I bar, b I bar composed with phi, right? And when I pull back the coordinate functions on Rn, I will get the components of phi, right? Okay. So what is phi star of d xi? See, applied to some vector v, this is going to be equal to dxi applied to d phi of v, right? And that is d of xi composed with phi of v, right? And xi composed with phi is the ith component of phi, which we're calling by abuse of notation also dxi, right? Is that clear? So phi star pulls back each dxi to the corresponding function on the manifold dxi, okay? So phi star of this dxi bar will be again dxi bar, okay? So there's an abuse of notation here. Is that clear? Yes?
Yeah.
Okay. In one case, the dxi bar means wedge product of the coordinate functions in Rn. Here it means wedge product of the components of phi. Okay. So from this, you see that bi composed with phi is equal to ai, right? Okay. So so what is d omega tilde? This is sum over I bar db I bar wedge dx I bar. So from this we get that ai bar is equal to bi bar composed with phi. Okay. And so what is phi star of d omega tilde? This is equal to sum over I bar. So phi star of dbi bar wedge phi star of dxi bar. Now, by abuse of notation, this phi star of dxi bar is again going to be dxi bar. And this phi star of dbi is going to be what? It's going to be d of bi bar composed with phi, right? Because it's going to be dbi bar composed with d phi, right? So by the chain rule, that's d of bi bar composed with phi, wedge dxi bar. So this is bi bar composed with phi is ai bar. So this is d of ai bar, wedge dxi bar. Okay. Is this clear? So this is our phi star of d omega tilde. This is our d sub phi of omega. This is our exterior derivative computed in a chart, right? It's just given by the same formula as in Rn, sum over I bar, dai bar, wedge dxi bar, right? Okay. But the claim is this is independent of the chart because of the following. So now suppose we take a point P in this open set U, and I take k plus 1 tangent vectors v1 to vk plus 1. Okay. At P. And I take C as a singular k plus 1 cube in M, well, in U, such that C0 is P and DC0 EI is VI. I goes from 1 to k plus 1. Okay. So then what I can do is the following. I can compose this cube C with the chart phi to get a cube in Rn. C tilde is phi composed with C. Okay. So this will give me a cube in Rn, okay, with some vectors Wi here. Yeah. So let me say Q is phi of P. Okay. So Q is equal to phi of P. This is a point in V in Rn. And say Wi is equal to d phi P of Vi. And this by the chain rule will be the derivative of the cube in Rn dc tilde at 0 of Ei. Okay. So now what do I have? Then I have that by the exterior, from the definition of the exterior derivative in Rn, I have that, so, okay. So how do we do this? Yeah, so Okay, so what is d sub phi omega at P applied to V1 to Vk plus 1? This is equal to, by definition, this is phi star of d omega tilde at P applied to V1 to Vk plus 1. But this is equal to d omega tilde, by definition of pullback, at Q applied to W1 to Wk plus 1. And this, by the property of the exterior derivative in Rn, this is the limit epsilon tends to 0, 1 over epsilon to the k plus 1, the integral of a boundary of C tilde epsilon, right, of omega tilde, right? But what is C tilde? This is phi composed with C, right? So this will be the boundary of phi composed with C epsilon. Okay. But now when I integrate over a face of phi composed with C epsilon, how do I do that? Remember what we have when we defined integration? You have to pull back the form by the map, right? So, okay, there's less than a minute. Let me stop this session and start a new one. Okay. So. Okay, so let's continue. Yeah, so this integral here, when I integrate over the boundary of phi composed with C epsilon, right, that is the same as pulling back omega tilde by phi composed with C epsilon, right, and integrating over the boundary of the unit k plus 1 cube. So when I pull back phi by phi composed with C epsilon, right, that's the same as first pulling back by phi and then pulling back by C epsilon. So this will become 1 over epsilon to the k plus 1, the integral over boundary C epsilon of phi star omega tilde, right? And this is phi star omega tilde is exactly by a definition, this is omega. So this becomes limit epsilon tends to 0, 1 over epsilon to the k plus 1, integral of omega over boundary C epsilon, right? So this last expression here, this is independent of the choice of chart phi, right? This does not involve the chart phi in any way, right? Is that clear? So that means, therefore, that this exterior derivative, which we defined a priori initially, I mean, using the chart phi, we find that its value actually does not depend on the choice of chart. Is that clear?
Yes, yes.
Okay. So therefore, the exterior derivative is well defined, independent of any choice of charts. Okay. Okay. So that's what I wanted to do. So we have the exterior derivative defined independent of any choice of chart. Okay. And then you can show that the exterior derivative on manifolds satisfies these same properties like in Rn. So d of df is 0, where f is any smooth function. And d of alpha wedge beta is again d alpha wedge beta plus -1 to the k alpha wedge d beta, where alpha is a k form, beta is an L form. These properties are local, right? So these follow from the corresponding properties in Rn. And also it commutes with pullback. So d of phi star omega is phi star d omega, where phi is any smooth map between manifolds. Okay, and omega is a k form on the target manifold N. Okay. Okay. And then you have from Stokes theorem for chains in Rn, you also get Stokes theorem for chains on manifolds. So if M is a smooth manifold, then for any k form omega on M, and for any k plus 1 chain sigma in M, the integral of d omega over sigma is equal to the integral of omega over boundary sigma. Okay. So this follows from the last property of the exterior derivative, this commuting with pullback, the naturality property. So the proof is very simple. You let I k plus 1 be the identity cube from the k plus 1 cube to itself. Okay, so this is a k plus 1 cube in Rk plus 1. And so for any smooth k plus 1 cube in M, the integral of d omega over c is the same thing as the integral of c star d omega over ik plus 1, right? And then by the naturality, c star d omega is the same as d of c star omega. And now c star omega is a k form in Rk plus 1. So by Stokes theorem for chains in Rn, this will become the integral over boundary of ik plus 1 of c star omega. And this, by definition of the integral, it's easy to see. This is equal to the integral of omega over boundary c. Okay. Okay, so that gives you Stokes theorem for chains in manifolds. Okay, it just follows for Stokes theorem for chains in Rn and naturality of the exterior derivative. Okay. Any questions? Okay, so as before, this implies that the exterior derivative is the dual of the boundary operator. Okay. And the dual of the boundary operator maps the subspace of K forms sitting inside K cochains to the subspace of K plus 1 forms sitting inside K plus 1 cochains. And because the square of the boundary operator is 0, that implies by duality the square of the exterior derivative is 0. Okay. All right. Okay. Okay, now I want to talk about what are called homotopies and the prism operator. Okay. So suppose M and N are smooth manifolds and H from M cross 0, 1 to N is a smooth homotopy. Okay. So that we get a one parameter family of maps H sub T from M to N. H sub T of X is H of X comma T. Okay. For X in M. So that, and let H0 be F and H1 is equal to G. Okay, so H is a smooth homotopy between two maps F and G from M to N. So then this defines what's called an associated prism operator P from K chains in M to K plus 1 chains in N. So this is defined as follows. So let C be a K cube, a singular K cube in M. So then we have to define PC. This is going to be a singular K plus 1 cube in N. Okay, so how do we define this? So PC of T comma X1 to XK, right? This is defined to be HT of C of X1 to XK. Yeah. So what's the picture? You have C is a K cube in M. So you think of C as defined on the bottom face of this K plus 1 cube. So that maps, it's a K cube in M. And then I have this homotopy right? So under the homotopy, I flow this k cube in M by each of the maps HT. So you sort of flow this, you map this k cube over to N and flow it along with time, right? Okay, so over here, the slice of the k plus 1 cube at a height t, this will map to HT composed with C. All right. Is the picture clear?
Yes, sir.
Yeah. So this is the prism operator. It goes, so we've defined it for k cubes, and then by linearity, it extends to k chains, right? So it's going to map k chains in M to k plus 1 chains in N. Okay. Okay. And so what will the integral over PC over this k plus 1 cube in N be? So we have to compute pullback by PC. So for that, we have to compute the derivatives of PC, right? So derivative of PC applied to the basis vector E1. This will be del T of PC. So this will be just del H del T at Cx comma T, okay? And the derivative of PC applied to EI plus 1, this will be what? This will be del xi of HT of Cx. So that will be d by the chain rule, dHT at Cx applied to dCx of EI, right? Okay, I goes from 1 to k. So therefore, if omega is a k plus 1 form on N and C is a k cube in M, then the integral of omega over PC will be what? This will be the integral, so dt dx1 dk, integral over 0, 1 to the k, and then integral over 0 to 1. Omega at, so PC of x, t comma x, that is ht of cx, applied to the derivative of PC applied to the basis vectors E1 up to ek plus 1. So that the first basis, the first image will be del h del t at Cx comma t, and then you'll get dHT at Cx applied to dCx E1 up to dHT Cx applied to dCx ek. This whole thing dt and then outside dx1 dk. And this thing, we can write this integral as an integral over 0, 1 to the k of C star of P star omega, where P star omega, this is going to be a k form on M. So, okay, so omega was a k plus 1 form on N. This P star omega, this is going to be a k form on M. So how is P star omega at a point P? How does it act on k vectors in M, k tangent vectors at P? So this is an integral 0 to 1 omega at ht of P applied to del h del t of P comma T, dHT V1 up to dHT Vk. Right, these are k plus 1 vectors in N. So omega acts on these k plus 1 vectors in N to give a real number. Integrate over T going from 0 to 1. So notice this will be multilinear in V1 to Vk and alternating in V1 to Vk, right? So this will become a k form on M. Okay. So the picture is like this, that if you have here so omega is a k plus 1 form on N, then P star omega will be a k form on M. So what you do is you have a point P and you have tangent vectors V1 up to Vk. Now you look at the curve HT of P. Okay, so that's going to be a curve going from f of p to g of p. Okay. And this point here is ht of p. All right. Now, when I take del t of this, that gives me the tangent vector to this curve. Okay. So this is del h del t. Right? At p comma t. Is that clear? That's the tangent vector to this curve, ht of p. And then I apply at each time t the derivative of ht to these vectors v1 to vk. So that gives me vectors here, dht v1 up to dht vk. Is that clear?
Yes, sir.
So now I have k plus 1 vectors at this point ht of p, right? So I can apply omega to these k plus 1 vectors, and then I integrate in t going from 0 to 1. Okay? So that gives me a linear function, a multilinear function of v1 to vk. Is this clear? Yeah. So that's how this form p star omega is defined. And if you look at this integral inside here, this is basically the pullback of p star omega by c star, right? Is it clear? Yeah, this is p star omega at the point c of x, right? Applied to dcx e1 to dcx ek, right? So that is nothing but the pullback of p star omega by c, right? Okay. So this is the integral over 0, 1 to the k, c star of p star omega. By definition, that is the integral of p star omega over c. Okay. Right, so what do we get? We get that the integral of omega over pc is equal to the integral of p star omega over c. Okay. So in other words, the pairing between omega and pc is equal to the pairing between p star omega and c. So this operator on forms that we've defined, p star, this goes from k plus 1 forms on n to k forms on m. This is nothing but the dual of the prism operator. So where you think of this k plus 1 forms on n, this is sitting inside ck plus 1 n dual, the k plus 1 cochains on n. And here you have the dual of the prism operator mapping to k cochains on n. Is this clear? So the dual of the prism operator is given by this formula, this p star omega that we define, and it takes the subspace of k plus 1 forms on n to the subspace of k forms on n. Is that clear?
Yeah.
Okay. Fine. So now what we want to do is look at an infinitesimal homotopy, a homotopy for small time. Okay. So how do we get that? Well, as follows. So suppose we take a vector field x on m. Okay. And we let phi t be the flow of x. Okay. So then I get a homotopy, or this is a typo here, from m to itself. So from m cross 0, 1 to m. This should be an m, not 0, 1 here. So x comma t goes to phi t of x. Right. So this is a homotopy between phi 0, which is identity, and phi 1. Okay. All right. So let P be the corresponding prism operator for this homotopy H. And now we define a small homotopy. Well, a small, that will be H of X comma epsilon T. And we define the corresponding prism operator P epsilon C of T comma X. This will be PC of epsilon T comma X. Okay. So this is nothing but the prism operator applied to the homotopy H of X comma epsilon T, right? You're just scaling the time by epsilon to look at a small time. Okay. So you're looking at the homotopy on a small time. So this is phi sub epsilon T of Cx, right? So in the picture, what is this corresponding prism operator going to look like? Well, if I take this will be, let's say, the image under C, and then my prism operator is going to map to a very thin prism. Okay, so this bottom side will be C, and this top side will be phi epsilon composed with C. Okay, this is my P epsilon C. Okay, if this is my 0, 1 to the K plus 1. Is this clear? Yeah. So you see the vertical sides of this in the vertical direction, this is more or less tangent to the vector field X, right? Because this phi t is the flow of X, right? So for small time, this moves in the direction of X. Okay. Okay. So this is what my K plus 1 cube P epsilon C looks like. So let's calculate this P epsilon star of omega, right? And divide that by epsilon. So what is that going to be? So that's 1 over epsilon into, so P epsilon star of omega, you follow the definition given above here. That will be an integral from 0 to 1. Omega at phi epsilon T of P, and then del T of phi epsilon T of P, and then d phi epsilon T of V1 up to d phi epsilon T of Vk, right? So del T of phi epsilon T, by the chain rule, this will be epsilon times X at phi epsilon T of P, right? Yeah, by the chain rule, I'll get an epsilon coming out. Okay. So this epsilon will come out of the omega and cancel with the epsilon here. So this will become the integral from 0 to 1, omega at phi epsilon T of P, X of phi epsilon T P, d phi epsilon T V1 to d phi epsilon T Vk. Now as epsilon tends to 0, these d phi epsilon t's will converge to d phi 0, which is identity, and phi epsilon t goes to phi 0, identity. So this whole thing will converge, the integrand will converge to a constant, omega at p applied to xp, comma v1 to vk. right? So this integral will converge to this quantity. Okay. And this you can see, this is a K form applied to V1 to Vk. This is a K form called the interior contraction of omega with x. Okay, where when omega is a K plus 1 form, then Ix omega, this interior contraction of omega with x, this is defined by just putting x in the first slot and then letting omega act on the remaining K vectors. Okay, so Ix omega at P applied to V1 to Vk is given by omega at P applied to xp comma V1 to Vk. Okay. So therefore, if I take any singular K cube C, then if I look at the integral of omega over P epsilon C, so this very thin cube, and I divide by epsilon, then this converges to, so this is equal to C, the integral over C of 1 over epsilon, P epsilon star of omega. And that converges to, this integrand converges to Ix omega. So this converges to the integral over C of Ix omega. Okay. So you can sort of see that in this picture, in the limit as epsilon tends to 0, integrating omega over this very thin K plus 1 cube and dividing by epsilon is basically the same as integrating omega, integrating Ix omega over C, right? Where Ix omega means you put a x in the first slot and then apply omega to the remaining K vectors. All right. Yeah, can you see that? Okay. So 1 over epsilon integral omega over P epsilon C. This converges as epsilon tends to 0 to the integral over C of Ix omega. Yeah. So informally speaking, the interior contraction Ix is in a sense the dual of the infinitesimal prism operator. Okay, whatever that means. Well, formally it means that Ix is a limit 1 of epsilon tending to 0, 1 over epsilon P epsilon star. Okay, so in that sense, it's a dual of an infinitesimal prism operator. Yeah. All right. Yeah. So why am I talking about prism operators? Because I want to prove what's called Cartan's formula, which is the following. So remember, we defined last time the Lie derivative of a vector field with respect to another vector field. Similarly, if I'm given a form omega, a K form on M, and X is a vector field on M with flow phi t, then we can define the Lie derivative of omega with respect to X. So this Lx omega is defined to be ddt at t equal to 0 of phi t star omega. Okay. So the point about this Lie derivative is the Lie derivative vanishes if and only if the form omega is invariant under the flow of X. So invariant under the flow of X means that phi t star omega is equal to omega for all t. Yeah. So of course, if phi t star omega is equal to omega for all t, then when you differentiate, you'll get 0. So then Lx omega is 0. Conversely, if this Lie derivative Lx omega is 0, then you can write this ddt of phi t star omega. This is similar to what we did earlier. You can write this as dds at s equal to 0 of phi t star of phi s star of omega. And then here t is fixed, s is varying. So this fixed phi t star, this is the linear map. I can pull it out of the derivative. This becomes phi t star of dds at s equal to 0 of phi s star omega. And this derivative is Lx omega. So this becomes phi t star of Lx omega. So if Lx omega is 0, then this is 0. So that means that ddt of phi t star omega is 0. So phi t star omega is constant. And then it has to be equal to omega, since phi 0 star of omega is omega. Okay. So therefore, phi t star omega is equal to omega for all t, if and only if Lx omega equal to 0. Okay. Now what we want is to get a formula for the Lie derivative. Okay. So suppose P epsilon are prism operators associated to the homotopy phi t, the flow of x. Okay. So now let C be a singular k cube. Then it's not hard to show, if you do this computation, this is a good exercise, you can do this, that the boundary of the k plus 1 cube, P epsilon C, this is going to be phi epsilon compose C minus P epsilon of boundary C. So you can see that from the picture. What is the boundary of this P epsilon C of this k plus 1 cube? So it's going to be the top face minus the bottom face. That is phi epsilon C minus phi epsilon composed with C minus C. So that's the top minus the bottom. And then you have the vertical sides, right? So the vertical sides will be the prism of the boundary, right? P epsilon of boundary C. Okay. Yes. Okay, so that's how you get this formula. So you can work this out. It's a nice exercise to compute this. Okay. So now we have omega our k form, right? So the boundary of P epsilon C, this is also a k chain. So we can integrate omega over this. And let me divide by epsilon. Okay. So this will be, since using this formula for the boundary, this will be 1 over epsilon, integral omega over phi epsilon compose C, minus integral omega over C, minus 1 over epsilon, integral omega over P epsilon of boundary C. Okay. Now, this left-hand side, by Stokes' theorem, this is 1 over epsilon, integral of d omega over P epsilon C. This is equal to this first term here, integral omega over phi epsilon composed with C. This is the same as integral of phi epsilon star omega over C. So then I can group together these two integrals as integral over C of phi epsilon star omega minus omega. And on this side, this integral over P epsilon of some chain del C is the same as integral over del C of P epsilon star omega, right? And I take the epsilon inside. Now you let epsilon tend to 0. Then this P epsilon C, I can move it, this integral, we saw that the integral of any form over P epsilon C divided by epsilon, that converges to the interior contraction, right? So, so this will converge, the left-hand side will converge to the integral over C, Ix d omega. Now this phi epsilon star omega minus omega, I divided by this epsilon. This converges to the Lie derivative, Lx omega. So the first term converges to integral of Lx omega over C, minus this last term, this 1 over epsilon, P epsilon star of omega, this converges to Ix omega, right? And then I have this integral over boundary C. So by Stokes' theorem, I can write it as an integral over C, d of this. So this becomes d of Ix omega, right? Is this clear?
Yes, sir.
Yeah. So now what do I get? I get that for every k cube C, the integral of this form, Ix d omega over C, is equal to the integral of this form, Lx omega minus d of Ix omega. So we know that k forms are determined by their integral over k cubes, right? Yes. If the integral over every k cube is 0, then the form is 0. So if the integrals of these two forms over all k cubes are equal, then the two forms must be equal, right? Therefore, we get what is Cartan's formula, that Ix d omega has to equal Lx omega minus d of Ix omega. Or in other words, if we rewrite this, then we get what is called Cartan's magic formula, that the Lie derivative Lx omega is d of Ix omega plus Ix of d omega. Okay. So Cartan's formula is often called an infinitesimal homotopy formula, right? Because it's coming by considering a homotopy and then letting the time in the homotopy become infinitesimal, right? Is it clear? Yeah, so this formula, in a sense, is the dual of this formula here for the prism operator, for the boundary of the prism operator. Okay. If I take duals everywhere and divide by epsilon, right, then this left-hand side will converge to the operator. If I take duals everywhere, and then this left-hand side will converge to Ix of d, and the right-hand side will converge to Lx minus dix, right? If I take duals, you see. So this Cartan formula comes by taking duals in this formula for the boundary of the prism operator, dividing by epsilon and letting epsilon tend to 0. You see. So the Cartan formula is an infinitesimal version of this formula for the boundary of the prism operator. That's all it is. Okay. It's just the dual formula. Is it clear? Yes?
Yes, sir.
Okay, so any questions? I won't do any more. We've just got about 2.5 minutes left. So if you have any questions, you can ask now.
Sir, can you please suggest any good reference for practicing exercise problems?
For exercises?
Yeah, for problems.
Well, I've given you quite a few exercises already today. You can just try and do those, right? So one exercise is to compute this formula, this boundary computation, boundary of the prism operator. And I don't know, I gave some other exercises. I forgot now. Just keep a note of the exercises I give. So I forgot. What are the exercises? Yeah, these properties of the exterior derivative, you try and prove them as exercises. Yeah.
Yeah, okay, all right.
Yeah, I think that you can do those as exercises. Yeah. Mhm. Okay, so we're more or less done with the preliminary parts on manifolds. We just have next time we'll just cover integration of forms on manifolds. So integration of an n form over an n manifold and Stokes' theorem for manifolds with boundary. That will finish the preliminary parts on manifolds. Then we will start talking about vector bundles and connections on vector bundles. then Riemannian geometry, and then we'll get to harmonic maps. So that's the plan for the next, for the rest of the course. Okay. Okay, then. So if there are no more questions, let's stop today and I'll see you on Friday. Okay.